So let's move on to a solution. Here, I'll present this one to you. Ultimately, this whole video isn't to introduce the first two, which are very well-known algorithms, but rather a slightly more particular sorting method that I haven't happened to come across elsewhere. So I think it's original enough to dedicate a video to it, which is a parametric type of sorting. So let's start from the beginning. Let's start with what parametric search is. Parametric search is a search that is based on the attempt to guess the position of an element in a vector, the position of a value in a vector, right? Search is an algorithm that, starting from a value, must give me the position. The search works like this, the parametric type of search. You try to guess the position from the value, assuming that the distribution from the minimum to the maximum is linear. So if, for example, I am looking for a value that is in the middle of the range between the minimum and the maximum, I immediately go to look at the middle of the vector's length. Obviously, it is not guaranteed that this hypothesis is correct, but this does not cause an error in the algorithm. At that point, you compare the point where I arrived, the value that was my first attempt at guessing with the value of the key, with the value that I need to find. If the value I found is smaller, you go in one direction, otherwise you go in another. It is obvious that, let's remember, the list must already be sorted in this case. But we are talking about searching. This is parametric search. Can't something similar be done for parametric sorting? Why not? Hey, first we distribute the values. Let's take a moment to see exactly what the minimum and maximum ranges are, and then we distribute those values parametrically. Now, obviously, what can happen here? Let's go see. Let's go see how we can manage to obtain this specific value. If I can just move this over, there we go. This menu right here, which allows us to adjust the parameters more precisely. Okay, so let's see how this parametric sorting algorithm is formed at this point, which can also be called linear sorting because it thinks about sorting the data as if they were linear. So at the beginning, the minimum and maximum are calculated. It's a two algorithms that are absolutely linear. Then we try to distribute the values. We assign a position to the values, pretending there is a linear distribution. What can happen? Well, we have considered two different cases. If we are dealing with integers, we can have two values, two or more repeated values. We could also have non-repeated values, but these intervals that I am marking here for you, in certain cases could also be different, include more values, and in any case, different values could end up in the same interval. And so we have, let's say, what we can call in jargon a collision. Let's see how it can be handled. After that, if instead we have real numbers, having the possibility of a collision is more difficult. We would have to have exactly the same value, which is not impossible, but it happens less easily. However, certainly, since the number of intervals cannot be very large, it can happen that we have two similar values that fall into the same interval, and various possibilities can occur. Either that by luck, they fall in an already ordered manner, meaning that these things here, the sublists that I have marked in red, are by chance already ordered. But that is a lucky case that we cannot take as an example, or in the general case, we have a disordered sublist that forms here. So what do? Well, we distribute the values as if they were linear. If there are collisions of any kind, well, we add the data into a sublist. So here we have a list whose elements are, in general, lists, sublists, okay? At this point, for each of these sublists, which could even be longer than 2 elements, it could even be made of 3 or 4 elements, though that's not likely. It's not the most probable thing. Well, for each of these sublists, we perform a traditional sort, but only if necessary. That is, if it consists of only one element, we do nothing. If it consists of 2 elements, we swap the pair. If it consists of more than 2 elements, we perform a normal sort. Of course, at this point, I have to write that this sorting step is O(n) squared, because in general, it could happen that with 3 or 4 elements, I have to perform an exchange sort. However, I am doing it in some very rare cases, and I am only doing it for very few, very small elements. And since the algorithm is quadratic let's say by breaking it down into many small pieces, smaller ones, in the end, I definitely gain from it, right? There is a law that I could have shown you, let's say, more easily. I mentioned it to you a little while ago, but anyway, just trust me on this small part. So we have the sublists, and then I just have to do the reconstruction. We have the algorithm divided into 4 steps, of which 3 steps are linear and 1 step is quadratic, but this quadratic step only occurs in a few sporadic cases. That's why if we look at our parametric sorting algorithm, we see that there is first the calculation of the minimum and maximum, the distribution of the values in this format, and then the reconstruction. In the reconstruction, I essentially ask myself, how big is the sublist that I find in each step? It can have 0 elements, it can have 1 element. In the case that it has 1, I don't have to do anything. It can have 2 elements. And in this case, I perform the swap directly, which is particularly fast if done in Python, thanks to the fact that a temporary variable is not necessary. It can have more elements. In this case, I perform a normal exchange sort. But this we could see it only comes into play very few times. Very well. Once this entire process is finally done, I will go ahead and reconstruct the final vector. Okay, now that we have that ready, let's go ahead and perform a quick test. This right here is the function we are using, and this is the specific call. Let's see exactly what it runs for me and if we get the expected output. So I ran it with some real numbers. This graphic format is simply because the environment finds, let's say, displaying all the numbers too heavy, so it only shows me the initial numbers. But I can see that at least the first part is sorted. Anyway, I tested it. You can try it too. Now I'll show you the code again so you can copy it while waiting for me to publish it on GitHub. Okay, so let's go back to the information the program gives us. The preliminary operations, that is the calculation of the mean, the linear distribution, take explicitly or almost explicitly twice the length of the vector. It's 2 times in -1. The number of comparisons is also a linear number. The number of swaps is very low. The total number of elements, the total of operations performed, which in this case are elementary, is 37,164 for 10,000 elements of the vector. That is, we have an average of 3.7 elements for each, 3.7 steps, for each element that we need to sort. And it's a very good average because in terms of order of magnitude, we are in the order of n log n. As an order of magnitude, clearly, it's not a precise calculation, it's an approximate calculation. So you see that this sorting method does not use recursion, but this sorting method allows me to perform this precisely the sorting of the list in a very simple way, certainly a bit more complicated compared to exchange sort, but with a very short number of steps. And there shouldn't be any memory type problems, for example, regarding memory management, at the idea of scaling it up to 1 million elements, 10 million, and so on. It is certainly a more efficient algorithm than the first 2 I showed you, especially the first one and the second one, depending on the implementation. All right? So we've taken a closer look at the problems that exist with these sorting algorithms. And I want to make a final point that is a bit detached from all of this. Why do we need to study these things in the age of artificial intelligence? But there wasn't even a need for artificial intelligence. In Python, you just need to call the sort function and we have the sorting. However, as I have always told you, we shouldn't delegate everything to artificial intelligence. We must be capable at least once of understanding how these things work. And then little by little, maybe we delegate what we are capable of doing. Only for time reasons, we delegate it to the various artificial intelligence models just to save time. It is essential, and for me it remains essential, that we understand this, what we are doing and how it should be done, and the theoretical problems that lie behind all these things that we do. All right? Thanks for everything. I hope that in the next videos I'll be able to produce something interesting about artificial intelligence. I'm working on it. So I'll see you next time, hopefully not in a year, but sooner, regarding a some application possibly, or some explanation too, some theoretical explanation as well about artificial intelligence. All right? Greetings to everyone. Goodbye.